That's great. So let's get started, everyone. So welcome back. So we are going to keep talking about gradient descent today. So at the so schedule, you kind of after the lecture on Tuesday, you should have kind of all the definitions you need. So in class today, we're going to talk about the actual algorithm. Actual algorithm is like extremely simple, but then we'll see it in Python with the example, which will be useful for your homework. As you'll see, the stuff I'm asking you to do in the homework, if you after you see the Python, should be quite simple what I'm actually asking you to do. And we will talk about the convergence of it. Okay, so what this might be kind of new way of thinking. Gradient descent is an algorithm, but it's not like a algorithm to try and sort data. In that, when you sort data, when you're done, and there's kind of discrete quantity kind of that you get at the end, and it's exactly right. Gradient descent is not like that, so we need to think about the kind of how well it's converging, and we will use the definitions that we talked about on Tuesday to kind of understand how fast it's converging. So we'll try and quantify this, and there are a couple of parameters that you'll need to. So if you can save that discussion until after class, that'd be great. All right. So thank you. And there are a couple of parameters you need to set in the algorithm. And so we'll talk about like how to actually set those parameters, right? So this will kind of be important practical knowledge. We're not going to yet connect it to data analysis that will come next week, and that will kind of show why all these bounds we need are going to be important. And that's going to be a little bit trickier, okay? So the homework 3, and the way we have the structure, homework 3 is due on Tuesday next week. And so it's kind of, I guess it's pretty soon after we've given you this Python code. I believe it should be simple to do what we're asking you to do. In homework 4, we're going to ask you to do the stuff we're talking about on Tuesday. Okay, so that's why it's kind of split like this. And that's a little bit trickier. That's going to be the trickiest thing going to ask you to do during the semester, I believe. You should be able to do it, but it's really the complete package of like starting from data to learning a machine learning algorithm the way almost all of machine learning works, right? The simplest version of that, but is kind of, you'll get to do that complete thing, and you'll have to piece a few things together. Okay, great. And then there'll be quiz 4 will just be on gradient descent. We're getting that together. Okay, so let's, any questions on kind of the structure of the homework? I have people mostly kind of gotten started on the homework 3. Okay, who maybe hasn't gotten much started on it yet? All right, so I'm hoping questions 2, once you read it and comprehend it, shouldn't be too hard. Question 3 shouldn't be too hard. Question 1, you're asked to actually implement the stuff for regression, right? And I've broken it down, so you're actually going to have to do some stuff in Python. If you haven't used Python before, this is kind of, it's kind of a bit of more of a jump than the other things. If you get stuck on a bunch of stuff, again, there's a tutorial on Python up here, linked off the webpage from last year. And this goes through a lot of the tools you'll need, and will answer a lot of the questions you will definitely have if you haven't otherwise tried to do this in Python before. If you have more questions, myself and the TAs are here to help you through it. I think as computer science students, you should be able to figure it out, but it's something that if you weren't mostly computer science students, it would be more than might be fair to ask you to do without going through it in a lot of detail in a lab or something like that. But I'm confident you guys will figure it out. You're all very, very smart students. So right? Yeah, great. Okay, cool. I get a lot of the best students in the university and in my classes here. So, oh, where'd that go? All right, okay, so let's get to gradient descent. Okay, and okay, so Tuesday we talked about functions. We're going to have a function that's going to go from RD to R. So it's going to give a kind of it's going to take in a d-dimensional vector, and it's going to output a value. And again, we're going to want to find the smallest value of this function. And then we talked about the gradient of f. This is also a function that goes from RD, right? So I evaluate this at any place, but the output of this function is going to be also an RD, okay? So the ventilation is on. I guess I don't know why the ventilation hasn't been on earlier, but okay. Okay, and so this function is precisely defined as, so I can define this in two ways. One is I can think of it as, well, let me just say it's a vector. So the vector output is the partial derivative. So at d alpha 1. So alpha 1 is the first thing in the input. So we typically say f of alpha, where alpha equals alpha 1 up to alpha d, right? And then I take f with the partial derivative with respect to the second parameter of the input, and each of these gives me one of the coordinates of this gradient. Okay, and in order to define this partial derivative, again, hopefully you've seen this in calculus. You basically treat this variable that's on the input, alpha 1, as the variable, and everything else is a constant, and then you just take the derivative. And we went through an example. We won't ask you to do anything that's very complex, and in fact, you'll often want to design a machine learning or data mining algorithm so that you can easily take the derivative. So you don't kind of come up with functions often. You'll design the function f, and you'll design it so that you can take the derivative easily, right? So in math classes, they try and come up with a function so that it's challenging for you. Your job as a machine learning person is to come up with a function so it's easy for you. Okay, so don't worry too much about the derivatives. At some point, you'll say, well, can I take this derivative? And I'd like to, and then you might need to dig into a little bit. But in this class, it'll all be pretty straightforward. It'll be like some polynomials, and we'll see on Tuesday why it's all these nice, why it's all these nice polynomials to work with. Okay, and then, so in order to define this, we talked about the directional derivative. Right, and where u is going to be some unit vector. So this is the directional derivative of the function f in direction u. And let me just write this definition up here again, because we're going to use it to think about how to interpret this derivative. All right, and this should be a form which should be familiar to the definition of a derivative. Right, so I just look at the function value. If function evaluated at alpha and at alpha plus HU. H is some small quantity which shrinks to 0. U is some direction I'm moving alpha, right? As opposed to a regular derivative in one dimension, there's only one direction you can move it. Now I can move it in any direction, but I keep the scale of that direction, right? It's a unit vector, so it doesn't encode length. H encodes the length. That length goes to 0. That's the directional derivative of this. And I can define each of these partial derivatives as a directional derivative. Okay, so why is this interesting? Because we're going to think about the derivative of a function. Let me try and draw some kind of function here. And I want to kind of give the sense that it's multi-dimensional, right? So think of this is R2, right? And there's one function value here, and it's kind of hard to draw, at least, right? I can think of maybe this, right? There's some kind of parabolic blue function here. And what we're going to do is we're going to take some point alpha, and we're going to evaluate this derivative, this gradient here, right? And the gradient is going to give us back a vector in our D, okay? So we're in R2, so D is 2, so it's a two-dimensional vector, which means that it's going to give some vector here. Now I can think of this vector as living in RD, but it's nice to kind of draw it on the curve here. And why this will be interesting is that there's going to give us something like a linear approximation of the curve. It's going to give us something like the tangent of the function value f. This is the function value f at this location. Okay, so and let me use this directional derivative to explain why this is the case. Okay, so we can also think of this directional derivative f of alpha as equal to the dot product of f of alpha, right, of the gradient of f of alpha, right, dotted with u. Okay, I can think of it as this, so I can think of this as this, so dot product. So the reason why that is remember the gradient is this vector here, and u is also going to be a vector, right? So u is going to be u1, u2, up to ud. This is also a d-dimensional vector. And the dot product is kind of, right? So it's also this vector, and what do? I multiply these components together, and then I add them up, right? That's what the dot product is doing. And the ui's all are between 0 and 1, and they add up to 1. That's what it means to be, so a unit vector, okay? Or they're square, by square, they're entries, and they add up to 1. But they're kind of components, right? There's kind of saying there's this u here is giving me some direction, u, right? And I'm saying how similar, well, this gradient vector I've actually written as a combination of these two directions, alpha 1 and alpha 2. Let me draw this a bit bigger here. This might be alpha 1, this might be alpha 2, and so the vector alpha is here, right? It's this two-dimensional thing. I have a component along the different axes, and then I take this u vector, and I take this dot product with this, and it's how much of this vector is along this dot product, right? So it's kind of saying, if I were to go in that direction, how fast is it changing? Okay, and so that's what this directional derivative is saying. And this is encoded. I can just take the dot product and this this can be recovered. Okay. Okay. So again, what we are going to want to do is we're going to want to move to the bottom of this function here, right? We want to find this minimum of this function, this alpha star, which is at the minimum. And so we want to move down, right? And I want to argue the gradient is going to go fastest up in the direction which is going the fastest way up. And if it's going fastest up, this is saying how fast is the function increasing, is what this directional derivative is saying. And if I want to maximize this over any direction I can go, then this gradient would be directional derivative is, I would want this to be large, right? And so it's known that if I maximize this, right, this maximum of this function over all u which has a norm equals to 1, well, that's going to be the direction. If I take the dot product, it's maximized when I go in the same direction as alpha. So I want, or as the same direction as the gradient. So this is maximized at u equals to the gradient of f of alpha, and I need to be a unit vector, so I just divide it. Okay, so if I choose this, this gives me the maximum direction here. Okay, and so basically this means that the directional derivative, I'm increasing the function the most when I'm going the direction of the gradient. Yeah. Oh, it's the norm of the gradient at alpha. Right, that's the norm. So I'm forcing you to be a unit vector. It's norm 1. What you do is you take that vector and you scale it by 1 over its norm, and that causes the norm to be 1. Yeah, great. So this means the gradient is kind of the direction of steepest ascent of the function, and so we're going to want to move in the opposite direction of that. Unless we're at like a saddle point or something, we can't guarantee that. But if we're at a regular point, then this is the case. We want to, very locally, at some level of locality, the best way down is going to be the opposite of the fastest way up. Okay, and okay, and the other way to think about this is if I take the dot product with a different u. The different u, I'm also kind of saying how fast is the function going up, but locally, that's kind of the increase. It's saying I'm giving kind of a linear approximation of this curved blue thing, of this curved blue function that's kind of curved here, but locally, if I zoom far enough in, it's going to look like this is like it's flat. The further, if I zoom far enough into this function, it's going to look basically flat, and this gradient gives me a full linear approximation. For any direction u, I want to say what's the tangent vector in that direction, then this I can recover it using this directional derivative. So it's giving me this linear approximation. Okay, good. Okay, so finally we can talk about the gradient descent. So the gradient descent algorithm. Okay, and again, the goal is going to be to min alpha, which is in RD of this function f of alpha, or often the case is actually the arg min of alpha in RD, and this is where we want to recover the actual parameters alpha, right? So I want to either find the minimum value of the function or the parameters, the arguments, which give me the minimum value. That's what the second one is saying, okay? And the algorithm we're going to use is Okay, let me write this out. So I want to first, so initialize, I need to set alpha, we'll call this alpha 0, some, so I need to start this, I need to start with some guess. Okay, so this is going to be our guess of what the answer is, and I'll write this out with using some sort of iterative term in index k, and we'll just start this out at 0, and then we'll just repeat a simple loop. Alpha, our guess after the k+1 step. So we started 0, so the first step, this will be the alpha to the superscript 1. I'm putting it in parentheses to indicate it's not a power, it's just an index. The lower index tells me it's a vector, which element it is. Okay, so this is just going to be the old guess, alpha k, plus some parameter gamma k, which could change every step, but we often will leave it just fixed, times the gradient of alpha at alpha k. Okay, and we do k get k+1. Okay, and that's basically the whole algorithm. And usually we will say until we'll run this until alpha k, the gradient, the norm of the gradient is less than some threshold. Some threshold, or I'll do it for t steps. I'll give some number of steps. So the code we're going to write today, and in your homework, I'll just say run this for 20 steps or run this for 100 steps. Okay, but we'll discuss why. In general, if you don't have any idea about the problem, this is often using a bound on the side. The magnitude of the gradient is a little bit better option here. And I mean, this is the whole algorithm. It's mostly you're just doing some initialization. You have a for loop, there's iterator, but it's really one line, right? It's this repeat, this one line. I have my old guess of the optimal value, and I'm going to, oh, I made a crucial but common mistake. This should be good. This should be a minus. I'm going to subtract some scale times the gradient. Okay? This guy is known as the scale quantity here. This is known as the learning rate. Okay, and you see here that the key thing we need is just this gradient. We don't actually need to evaluate the function anymore, right? We just need to evaluate the gradient of the function. But this is the whole algorithm, right? I start with some guess what I have. I look at the gradient and I go in the negative direction. I go the steepest step downhill. I make some step. I scale it by some learning rate, and I get a new guess. And I keep repeating this until I think I'm done. Okay? Yep. So great. Yeah. So what is the point of the learning rate, right? So I could just set this at 1, so it's not there, right? And then just step down. Well, sometimes if you set the learning rate too low, you're going to make too little progress every step. Sometimes if you set it too big, you're going to make too much progress. You're going to jump right past the answer. Actually, so let's look at some code and actually see this now. Okay, and this will help answer your question. Okay, so we're going to import just NumPy and linear algebra. We're going to plot some stuff. So here's my function. I'm using here a two-dimensional function, just like on your homework. Instead of alpha, I just have x and y explicitly. So you don't need to worry about the vector algebra at this stage. And the function is 0.75 x minus 1.5 at quantity squared plus y minus 2 quantity squared plus 0.25 xy. Okay, this is a quadratic function. Neither x or y is ever raised to a power more than 2. Okay, and which will be next? It's going to be, and all the coefficients of x and y are positive, so it's going to be something kind of like a parabola, but in 2D. Okay, and so I've just defined this function here in Python, and then you need to take the derivative of this function. Okay, the gradient, in fact, and I've computed the two partial derivatives here. On your homework, one of the things you'll need to do is take the derivative of these functions. They're polynomials. You should be able to do it. Okay. Right. And so I've just, okay, so we're going to plot it. We're going to plot a two-dimensional picture here. And so I need to set up these line spaces between 0 and 5 with 26 kind of points in between. So every 0.2, I'm doing that for x and y, and I get this thing called a mesh grid. This mesh grid kind of combines these together. This is just some Python kind of standard way for plotting. And I'm going to evaluate the function. It's for all values of x, y in this mesh grid, right? And this is going to allow me to plot it, right? And then, yeah, and then this is going to tell me I'm going to draw these cool pictures with these level sets. I'm going to draw 21 different function values between 0 and 20. In your homework, you're going to probably need to adjust this a little bit. So you're drawing the relevant part of the functions. Okay, so in your homework, it'll be helpful to play with these parameters. So you're kind of scanning to make sure you're drawing the relevant part of your functions, and you can see what's going on. Okay, then let's actually set up, initialize everything. We're doing all this stuff before we get to the actual algorithm. I'm initializing at a point x equals 5, y equals 4. We're going to take 10 steps. Okay, and we're going to, and we're going to, learning rate for now is going to be 0.2. I'll change this later and you'll see if it was a good or bad choice if we choose a different learning rate. This is so we can draw a nice picture of the actual descent. Okay, so I'm going to keep track of the values. In general, you don't need to keep track of the values, but it makes for a nice picture. Now I can finally run the algorithm, right? Just run for num iter 10 steps. Every time I take the value, my gas V, subtract the gradient at the current value minus this minus the learning rate, and I store it to my values, right? So the algorithm itself, super, super simple. Okay, and now we're going to plot this. Okay, this plotting, it's going to draw a contour plot. So I'm going to draw a line for every fixed function value. I'm going to color those lines so you can kind of see the function, right? So the smallest values are in the middle here. And as I get further out, I draw a line. Every line, the value is the same on that line, right? So this gives you a good picture of what this function looks like. Okay? And I'm going to also plot these values where I'm going to draw a line in red, and I'm going to draw the actual points I'm stopping along this line. These are the values I'm getting in blue with the dots. That's what these two lines are. And then, and I'm computing the final norm, the last step. I get a gradient, final gradient of 0.342. And if that is below my threshold, I can stop, right? So that could be a stopping condition. Or you might want to print that out at every step along the way. And it's title, okay, and so here's the plot, right? So I started at 5, x equals 5, y equals 4 up here in the corner, and I'm coming down here towards the minimum to be right inside all of those circles there. So how do you think this did? Yep.
Is it not quite exactly reaching?
Yeah, it hasn't reached the minimum, right? So, okay, well, so what do you think I should do if I haven't quite reached the minimum, right? Well, how could I change it, the parameters, to do better? All right, I can increase the number. Yeah, I have the two parameters, num-iter, I set to 10, and the gamma at 2. Let's fix the number of iterations. I think 10 should be enough. Let's increase gamma here. I can't see it. Let's increase this to 2. All right, let's see what happens. Okay, I've increased the learning rate to 2 now. It's slow. Let's go. Oh boy, what happened here? I made it. Okay, let's try not increasing it so much. Let's try increasing it to 1. I know what happened, but it's easier to change it than to explain right now. Let's make it a little bit smaller. I think 1's not gonna. Yeah. Oh, okay. This isn't good. Right. Okay. So we started out here and over on the right side. We jumped all the way down here. Right. That's a bigger jump because we ignored the learning rate. Right. We set it to 1. And then from here, well, we realized we're too far. It's off the area we plotted even. So it jumps back this way, and then it jumps here, and it's actually getting closer. I bet if I ran this long enough, it might actually find the solution. But this seems like the learning rate is too high, right? So let's try this again here. What should I try as a learning rate? 0.7. All right. Hold on. Okay, let's see how we're. The anticipation. Okay, good. All right, 0.7. I think we found the minimum here. We did pretty good. The final gradient now is 0.004. So that's the gradient is small. At the minimum, the gradient should be 0. Okay, so the norm of it should be 0 in all coordinates. So the norm should be 0 as well. So that's a good indication that we're getting small. So we've done better than 0.2.
Did it still overshoot or?
Yeah, it's still overshot. Yeah, this is probably not what you'd like to see. It's kind of every step we're kind of getting lucky, and every step it's kind of overshooting, and it's eventually getting there. But we're jumping past. Like if all I know is I should go in this direction, and I should probably stop around here, right? So I'm kind of overshooting a little bit. And so I think if I did a lower learning rate, I could do a bit better, in fact. Let's try 0.5, see what happens. All right, okay, yeah, this one's looking a bit better. I've got 0.03. So the final gradient is a bit smaller, but I've gotten there. I've made progress, more progress every step along the way. I'm not really ever overshooting. I probably want it a bit smaller. Let's try 0.4. This might not get an answer quite as good. The 0.5 is still a bit aggressive, maybe. So I might get like a smoother curve, which might be more like what you expect. It's kind of curving in here. This final result is not quite as good, but this kind of curve in here kind of looks like it's very nice, I guess. Right? Okay, so you want to somehow, it is important how you set this learning rate, right? If I set it too big, it jumps way off the screen and it might not ever come back. It might keep jumping further and further away. If I say it too small, it's not going to get there, right? If I set it to 0.1, it's going to be even shorter. But if I set it just right, it's going to converge, and in under 10 steps, I got very close to the right answer. right? So this is 0.1. You know, I clearly did not get here. That was, eventually I will get there, but you know, it might take 40, 50 steps. If I set it way too small, it might take thousands of steps. And I don't have, you know, it's pretty fast in this case, but if you're running kind of a much more complex system where the function is gradient is much more expensive to evaluate, you are not going to want to kind of take hundreds of steps. You'd rather take 10 steps, right? Okay, so the learning rate is kind of an important question. Yeah.
There's a good question in the chat.
Oh, okay, great. Okay, how hard would it be to modify the function to allow the learning rate to be reduced over time? Yeah, so we are next, in fact, the rest of the lecture will be talking about kind of how can you choose the learning rate and when, what do you need to know about the function so that you can guarantee it converges so quickly, right? So we are going to talk about that. Sometimes you want to decrease the learning rate over time, but generally you want to, if you assume the function is kind of a fairly nice parabola, you kind of, you often want to kind of stick to a kind of a one learning rate, and just once you find that right learning rate sweet spot, you just want to keep, you just kind of want to keep going with that. There are other techniques that try and determine every single step, what is the best learning rate I can do. If you remember this this one with 0.5, right? This one probably converged the fastest, and it kind of, the first step here is going to kind of hit right on the minimum along that line, right? Given that I'm following the gradient, then I want to hit the minimum I can possibly hit. If I kept going, you know, maybe I overshot just a tad, but if I kept going, I was going to go up, and if I was shorter, it's going to be higher. So this first step is about as good as I can do. But the second step, you know, I have the right direction. I could have gone right here, which would have been even better. So I could have done even better in the second step, but the first step is pretty good. So I might want to adjust this every time. Great. So that's what we're going to talk about the rest of the lecture, right? How do we set these kind of these parameters? Okay, good. But for your homework, you want to kind of play with the parameters and maybe some of the techniques on the functions I gave you and see how well you can do, and adjust and play with the parameters. You need to take the derivative and then play with the parameters in the step 17 here to make sure your plot is in the right zone. I don't think we intentionally set it, so it might not be the optimal thing. So you're forced to play with them and see how the parameters work. Okay, good. We can come back to that after we talked about some of this stuff. All right. Let me first say something very briefly about the stopping condition. So either we do the number of steps t. This is if we are so time constrained. Sometimes actually you get a more stable solution to a data analysis problem if you stop before it's actually converged. But we're not going to get into that in this class so much. The other one is if I look at the norm of the gradient is less than some threshold, we should remember that at the optimal alpha star, that alpha of alpha star is going to be equal to the all zeros vector, which would mean that this guy is going to be, the norm is going to be 0. So as we get closer to 0, that's an indication we're actually closer to the minimum here. This is also useful to think about, because that means this blue box here, the gradient, that vector is going to be a smaller scale as I get closer to the minimum. So even with the fixed learning rate, I'm already taking smaller and smaller steps as I get closer. So I'm kind of honing in a nice way, even without adjusting the learning rates. Okay, so there's a suggestion of kind of having the learning rate go down as you get closer. Well, the gradient itself is already kind of is regulating that in some sense already. Okay, good. So and so these are good things to print out to make sure you're actually converging. In this example, in the 2D, you can draw pictures and you can kind of visually see what's going on. But in higher dimensions, that's much harder to do. So you often just print out quantities like this to kind of, you should expect the norm of the gradient to be decreasing as you go, and the function value. But you're not necessarily computing the function value, you're only computing the gradient. So printing out the norm of the gradient is not additional kind of computational overhead. Okay. Okay. The learning rate. Okay. So to talk about the learning rate, right? So so how to choose, kind of we need to talk a little bit about functions and like convexity and stuff like this again, in order to understand how we should choose the learning rate. And before we talk about kind of convexity, let me first give a definition here. Okay, so a Lipschitz property, we say a function, and I'll call this G from RD to, I'll just define this generally, RD to RK is L, so Lipschitz, if for all P and Q in RD, that we have that G of P minus G of Q is less than L times P minus Q, right? Okay, so let's look at what this says. I'm taking a function G, I'm evaluating at two spots, and I want to say the difference in the function value is less than L times the difference between these points. If you think of this as P, as U equals P minus Q over the norm P minus Q, right? So this is just some direction, and we set Q equals to P plus U times H, right? So now this looks like this directional derivative, right? So now this is just G of P minus G of P plus U H, right? And I can divide this now by this distance between P and Q is now exactly H, right? Is H, and I want this to be less than L. This means that the derivative, directional derivative in all directions, which means the gradient of this is always less than L. Okay, this will be useful. I use G here instead of F because this will be useful where we're going to let now the gradient equals to G. So we're going to be talking about the gradient of the gradient. So the norm of the second derivative of F is what we want to bound on. Okay, and we're going to say if we assume that the the gradient of F is L, so Lipschitz, and we set set gamma to be less than 1 over L. Okay, so gamma has to be smaller than 1 over the second derivative of the function, or the Lipschitz parameter, how quickly the gradient is changing, right? If I set gamma is less than that, so if I set it small enough, right, then the gradient descent will converge. Okay, so I won't bounce around away from the minimum. Okay, so I won't bounce around too far. This is true. It'll converge to a stationary point even if it's not convex and I just have one local minimum. It will converge, and if it is convex F, then after K equals to C over epsilon steps, I'm going to satisfy that F of alpha K minus F of alpha star is less than epsilon. Okay, so here's kind of the property I can say, that the function value I find after K steps is going to be the difference from the optimal function value. So it's going to be larger. It can't be smaller than the optimal function value, but the difference will be bounded by epsilon. Okay, and there's some constant C here. There's some constant value C. This constant will depend somehow on the scale of the function and where my initial starting point is. If I start at the minimum, then this C is 0, but if I start far enough away, it might be bigger. But assuming I don't start too far away, and C somehow scales with, if I multiply F by 10, then C will multiply by 10, right? So there's some scale constant in here, but it means that after basically 1 over epsilon steps, I'll have epsilon area, right? So I'm going down at this rate, and I will eventually converge. If I set this learning rate to be small enough with respect to the bound on how fast the gradient is changing. Okay. Now I can't say how fast the function is changing, right? If I have if you think if I just have like a parabola, and think of just y equals x squared, right? Y equals x squared, as I get further away from 0, y equals x squared goes off to infinity, and the first derivative goes off to infinity, right? But if I take the second derivative of y equals x squared, it's a constant, right? So it's saying that that means for a typical parabola, L is just an absolute constant, right? If I just have a typical, if I have a quadratic function that somehow it's some polynomial raised to at most a degree 2, this L is a total constant here, and often I might actually know what that constant is. I can work it out depending on how I build F. The second derivative will be bounded. If I set the learning rate sufficiently small, then I will converge. Okay, so if I set it small enough, I will eventually converge. If I set it, just at this 1 over L mark, basically, it'll converge about as fast as I can guarantee that it will still converge. If I set it too small, it will converge, but it's going to take a lot of steps. Okay, and so if I set it smaller, then the C will is going to be bigger too, right? I'll need more steps, but at that rate, it'll be converging at that rate. Okay, so if the second derivative is bounded and a quadratic function with bounded second derivative, it will converge at this rate. Okay, so we can say, yeah. Yeah, so C is C depends on a number of different quantities, and we won't actually have C. It'll depend on where you start, something about the scale of the function, and if you undershoot the learning rates, then it'll be bigger too. So so we won't know C. We're gonna have to, like, if you're in 2D, you can plot it like I did in the example, but you can also you can look at the norm of the gradient and the function value and see how that's changing and try adjusting it. Okay, so this is the first thing I say. This is not the last thing I'll say about this. So kind of we'll keep giving you more advice on this. So great. Okay, so we'd like to say something stronger, and so this basically worked well for a convex function, but we're going to need now what's called a strongly convex function, and this is basically like they call it strongly here. The thing of this as strictly convex function. Okay, so this is so we had this strict definition earlier. So it's basically going to mean a strict, and so but we're going to define this so like a particular way. We're going to say that f is an eta strongly convex if the following property holds. So we're going to say for all alpha and p in Rd, these are two potential points. Then we're going to have that f of p is going to be greater or equal than, let's see, f of alpha, right? But plus the gradient at f of alpha minus p minus alpha. Okay, so this is kind of the linear approximation. And then we're going to also have plus eta over 2 p minus alpha squared. Okay, so we're going to say f of p will always be greater than this this quadratic approximation of the function, right? So this first part here, you know, this is our linear approximation that we talked earlier about, where the gradient just gives you just a linear approximation. As I move further away from alpha with p, I can potentially get larger. But then but I also want to have this quadratic approximation. So now instead of approximating a function at a point with a plane, I'm going to approximate it with a piece of a parabola. And I'm saying I'm always going to be above this piece of this parabola. Okay, so let me try and draw a picture of this. All right, so let's see. So let's see, we're going to have what? So we're going to have a blue function here. It's going to have, let's say this is going to be our function f. So this will be, let's pick here, this will be our point alpha, right? And then we want to evaluate it at some point p. So alpha is where we have this approximation, right? So this point is going to be f of alpha, right? That's the point here. And okay, if we have the gradient, we're going to have the linear approximation here, right? So this function is going to be a linear approximation, this first one I've drawn, which is going to be f alpha, where we're starting, that's the function value we're starting at, plus gamma of the gradient at alpha p minus alpha. Okay, so this green line is like a linear approximation. It's a line I'm saying, as I move away from alpha, I'm decreasing if I go in this direction towards p. Okay, so I'm saying f of p is going to be above this. That so far is satisfied. If it's a convex function, it will need to satisfy this property, that the linear approximation will always be below it. Okay, and I get that from convexity, but I'm going to want something stronger. If it's, okay, let me then write, if it's a Lipschitz function, right? If it's a Lipschitz function, what that's saying, or the gradient is Lipschitz, that means that I can draw another parabolic function. And this one I want to be always bigger than. I say it doesn't curve faster than this one. This one is F alpha plus the linear approximation, P minus alpha, but then plus L over 2 times the distance squared. Okay, so this is if I can always draw a parabola with a the coefficient from the quadratic term is L or L over 2, then this gives me a Lipschitz approximation. This means the gradient is L Lipschitz, and that means it doesn't curve too fast. The gradient does not change too fast. And this means I get this one convergent, but the strongly convex function, which is the property we're talking about now, is saying that there's another parabola that sits in here, and I can set this for any point alpha, right? So this orange function is now f of alpha plus the linear approximation plus eta over 2 p minus alpha squared. And this one should always be lower than the function value, right? So f of p should always be above this, right? So if I look at value p, I'm going to always have the linear approximation is below, the Lipschitz bound is always going to be above, it's not curving faster than that. And strongly convex with the parameter eta is going to be this other parabolic function, other quadratic function, it's always below it as well. So I don't only get this linear lower bound, but I get a quadratic lower bound. Okay, so this is what this strongly convex property means. Okay. Okay, so if I have this property, I can say something much stronger about the convergence, and this will give rise to an algorithm, in fact. So if f is eta strongly convex, and the gradient is L so Lipschitz, and I set gamma the learning rate. If I set this let's see, I set this less than and I'd like to set it as large as I can, but so that it's less than 2 over L plus eta. Okay, so it's basically the average of L and eta, 1 over the average of L and eta. That's what this is. If I put L plus eta over 2, that would be the average. So it's 1 over the average of them. So if I set less than that, then after, for k greater, for this number of iterations, right, equal to c times log of 1 over epsilon, then I'm going to have this same sort of bound. Right, okay. So if I have this strongly convex property, I'm going to say after roughly log 1 over epsilon steps, right, log, this is the number of steps, I get this epsilon error. And again, the c depends on some scale quantities, how far away I start, kind of the condition number, which is the ratio between L and eta. Okay, so it's going to depend on some of these quantities, but the important thing is that it's going to decay. The error is going to go down as a function of log 1 over epsilon, after log 1 over epsilon steps. Okay, so how should we think about this? Let's say c was 1 and it was a log base 10, right? So let's say, imagine c equals 1 and log equals log base 10, right? It also depends on the base of the log that goes into c, right? Then what is this saying? It's saying my error is, it's like if I want the error to be so many k digits of precision, right? I need to go k steps, right? So my error epsilon, it's going to be 0.000 times, you know, right? So the first k digits of precision, and it depends on how far I start. Let's say I started at a value 1. I'm getting k digits of precision after k steps. That's really fast. Okay, I'm going to converge at an extremely fast rate if this is the case. Every step I make, I basically resolve an order of magnitude of how close the function is. Okay, now if c is bigger, let's say c is 3, that basically means I need to take 3 steps to resolve one digit of the right answer. Okay, that's still pretty good. If it's base 2 instead of base 10, you know, it's some constant number of steps. But every constant number of steps, I resolve 1 digit of the function value. This is really fast a way of convergence. Yeah.
I don't know if it just means, but I'm fairly confident exactly what like some of the equations.
Yeah. So it's a little tricky because we introduced it. Great. So we introduced this. Where do we introduce Lipschitz function? Here. Great. We introduced it for this function g. Yeah, and this function, we're going to need this for the gradient, but this is a more general concept of a Lipschitz function. This comes up a lot of places in analysis. It basically says, if I evaluate this function at 2 points, and those 2 points are close together, then the function values must be close. Right? So what I've done here, in this example, I related it to the gradient, right? The directional derivative. Let's say I took these 2 points, P and Q, and I'm going to create some vector U that goes from P to Q. Right? So if I scale this, and how far away Q is depends on some parameter H. Right? So if I take, so I want to say if the points are H distance away, right, this quantity is then H if I do it this way. Right? So then what I've done is I've divided by H to get this equation that is saying that the difference between the 2 function values divided by H is less than that. So that means that if I draw, there's some function on top of here, right? There's some function value, and it could be a vectorized value, right? As I'm evaluating that at every point in RD, and the value doesn't, if I don't move very far from where I evaluate, the function value doesn't change very much. So what this should say is that and I'm applying this to the gradient, right? So, okay, so let's, does this kind of help with this Lipschitz concept? It means that the function, it can't change very rapidly. It's, so if I have, so G, I can think of this is RD, but I'm just going to draw it in R1. And so I'm going to have some function, right? And so this is the function G. And so where is the Lipschitz constant the highest? That happens right here, where this is P and Q, because the slope is really high. Right? G of P, G of Q, right? The function value changes very quickly here. And so this makes it hard to, if I were to do a stepwise approximation, there'd be a big jump in the steps right here. And so that makes it hard to, if I'm trying to minimize the gradient, I want that to be not changing too quickly. That means if I move a little step, my direction doesn't change too much, for instance. That's one thing that comes up. Yeah.
So the L value of that Lipschitz
Yeah, it's the maximum over all points on the function. So I say everywhere the function is kind of well behaved, right? And what this is saying is that I can fit, when I apply this on the gradient, I get this red curve. I can, every point alpha, I can fit a parabola that's adjacent, that's tangent at this point, alpha at f of alpha. And that parabola has, the term in front of the quadratic part is bounded by L. So I can always fit a parabola that's not too steep. You know, so its second derivative is not too large, right? Because when I take the second derivative, the 2 comes out and cancels the 1/2, so that's why the 1/2 is there, right? It's a bound on the second derivative of the function. And that should be true everywhere for the blue curve. So the blue curve, everywhere the second derivative is bound. But this is not just the second derivative, it's the second directional derivative for all directions. Yeah, so that gives me an upper bound of the function. The orange one gives me a lower bound. Okay, and if I have both of those, then I get this really fast convergence rate. Okay, and this will correspond in linear regression. We'll see on Tuesday next week, when I have basically when I can invert my matrix. It's going to be full rank. As long as that matrix is kind of well behaved, then I'm going to be able to actually converge really fast with gradient descent. Okay. Yeah, great. Okay, cool. So this tells me I should be able to get this really fast convergence rate. I still haven't told you really how to pick gamma. I mean, if I know if it's, I basically set it equal to 2 over L plus eta. If I know what L and eta are, if I don't know what they are, still haven't told you what to do here. And I promised you I would give you some hints on this. All right. In case I promised you, okay, I'm promising you now, and now I'm going to give you the hints. Okay, so okay, so there are kind of 2 approaches to adjusting gamma, the learning rate. Okay, the first approach won't use the strongly convex idea, and the second approach will. The first approach is just called line search. Okay, and that's for this idea is every step I need to do alpha equals alpha minus gamma, right? And so these quantities are given ahead of time, right? In the blue, those are given ahead of time, and my goal is to minimize. Let's call this just alpha prime. Is to minimize f of alpha prime. Well, the nice thing, before I have this multi-dimensional search, right? I have to search all possible parameter values of d, the d parameter values of alpha. But once I fix the gradient, then I only have one parameter value, gamma. So I can actually restrict the search to a single line. I'm at alpha. I'm going to go to alpha prime, and it's going to be in this direction, right? So this tells me the direction, and I know my solution is somehow restricted to lie on this line, and I can have I can think of there's some function f here, and so the minimum of the function f might be at this point, right? So I can just search on this line. So I can say I want to find r min lambda, which is just gamma, which is just a single scalar value now of f of alpha minus gamma, right? And again, this quantity and this quantity is fixed. So I'm just solving for gamma here, and I can basically do something like binary search. So I can just solve, so often people do something like binary search. I put in the book in the notes something about the golden section search, which is a little bit kind of a way to do that, because that's a little bit better than binary search in this setting. Sometimes you can actually write out these equations, and you can actually take the first derivative and set it equal to 0, right, and solve for it optimally, right? So sometimes you can have a closed form solution for this, right? So I'm going to set kind of this gamma star equal to this, and I do this for every single step I do. So having a binary search inside of an iterative algorithm is kind of will slow it down a little bit. So you would do this, it's going to be slow, but if evaluating the gradient is very expensive, but say evaluating the function is not, then I only have to evaluate the gradient once, and the function evaluation I can do 10 times and get a pretty good value, yes, of gamma, right? So this is one way of kind of a more, kind of a better way of choosing gamma. It doesn't use any of the mathematics we talked about, but this is one way to do it. This is not commonly used though, because it slows down every step. Okay, so this is often too slow, but it's very effective. So hint, hint. Okay. Okay, the other way of doing it is an adjustable rate algorithm. Okay, and this is where I'm going to, I'm going to start with, say, some gamma equals to, say, gamma naught, some initialization. And I'm going to start this a bit, so a bit larger than I think is the right answer. Okay, because I'm never going to increase the learning rates, so I'm going to decrease the learning rate. So I'm going to do sometimes I'm going to set gamma equals to gamma times what do I call this, times beta, for some beta, say between 0.1 and 0.8. I've seen recommended 0.75, for instance, okay? So I'm shrinking every time, sometimes, and there's gonna be some condition I'm gonna check. And if that condition is violated, meaning I think I jumped too far, like we saw in the example, I'm gonna say, gamma's too big. So let me decrease gamma a little bit. Now I don't necessarily need to actually backtrack my gradient descent algorithm. I'll do this inside of the gradient descent with a simple check. Okay, and so condition under which I shrink my gamma is going to be as follows. It's going to be as if f alpha minus gamma times the gradient at f alpha. If this is greater, let's say greater than f of alpha minus gamma over 2, times the square of the norm of the gradient. Okay. So, okay, if you remember back to this formulation, the sweet spot was when gamma is basically the midway, 1 over the midway point between the upper and the lower bound on the second derivative of the function. Okay, and so the second derivative of the function showed up in the approximation of f of alpha plus some linear approximation, which we're going to ignore, plus L over 2 times so times this difference squared. Okay, and so this difference squared of the step, I'm going to approximate that. How far do I move? Well, that's roughly proportional to the gradient, right? P is going to be chosen from alpha. I'm going to move the gradient times some learning rate, and so that's right. So that's basically what's going on here. This is my guess f of alpha, and then I'm going to say my update based on the gradient. If I have a good quadratic approximation with my learning rate, it's going to be basically the size of the gradient. The update is going to look something like that. The size of the gradient. So I'm at, let's see, at alpha here, and I'm going to kind of guess I should move this far. Okay, so this distance I moved is roughly proportional to gamma times some effect. And what's happened here is I've gone past the minimum of the function, right? So that's saying, so yeah, well, let's pick, I moved out here. This is some point, a gamma distance away, and I've passed the minimum of the function. So the function value at this point, if I actually, so this is how much I move. If I reevaluate the function value, well, then it's going to be larger. Right, so this function value is larger than whatever my approximation was. So that's saying I jumped too far, right? So this is kind of the right way to encode, did I jump too far based on the function values and some sort of quadratic approximation that the learning rate is implying here. And so if I fail this check, so if, then I said gamma equals to beta times gamma, and that's decreasing gamma. And eventually I will decrease it until I'm sufficiently small, so I'm going to get, if I have a quadratic approximation, if there is a strongly convex function, I will eventually tap into that parameter setting where I'm going to get this really fast convergence. Okay, so if you have a strongly convex function and you use this adjustable learning rate, then you will eventually adjust the parameters, the learning rate, so that you're in this regime where you converge basically a constant number of steps and you resolve one digit of precision. And it will converge eventually if you use this adjustable learning rate. Okay. Now there might be some startup costs if you started way too big. They take a number of times in order to get down. And if you start too small, well, I can't get any bigger again. So I might have to take too many steps. But that's only going to go in the constant factor. But I'm still going to get this logarithmic kind of improvement, which is going to be is really fast. Okay, great. So one more thing I should say, this in like the optimization literature, when I get this sort of improvement with the log rate, this is called linear. Is called linear convergence. Nowhere else is it called linear convergence except when people discuss this, because they often plot stuff on a log scale and it looks linear. But so in case you see something called linear convergence in some other optimization class, that's what this is. Although I think that name doesn't make a lot of sense. Okay, great. Well, we'll stop here and we will, hopefully that the code should be useful for your homework due next week. And we'll connect this to data analysis and put all these things together on Tuesday next week as well.